please remember that when you increase or decrease a place and then 2 places and 3 places, that's actually an exponent, a factor of 2. So it's 2, 4, 8, 16. The factor that's used to change the number of networks and the available addresses in each of those networks. We were just stating here that even though both of these devices have the exact same network address, each of these function in a very different way, because in this case, with a /24 subnet mask, this device says, oh, I belong to a network, and anything that has a 192.168.2.3, that's my network. They're my neighbor. I can talk to them because they're on my same network. This device has a similar but different view of things. This device, because it has a /16 network, says, oh, I can talk to anything on the local wire or broadcast domain if it has a 192.16. So long as it has this, that's my zip code, that's my neighborhood. It's a much bigger neighborhood. So this device could talk to devices that had a .22 or a .202 here, right? This device could not. If there was a .22 or a .202 right here, this device would say, yeah, they don't have a .23, so they don't belong to us. They're not in our neighborhood. That's how IP addressing works. You have to belong to the same network, neighborhood, or LAN, right? And in terms of the IP addressing, that's the third layer of protocol. The physical wire, they can all hear and see each other, but because of the networking addresses, you can control and limit who gets to talk to who. And hackers love to mess with these subnet masks on purpose, right? Let's go back to where we were covering on Wednesday. So we were talking about the 2 layers, and we got down to what happens when 2 systems are talking to each other. Now, one of the things that is subtle, we're going to spend more time investigating in our next modules, is this idea of encapsulation. So on the wire, we have signals, and the signals are bundled into chunks of data, ones and zeros. They represent ones and zeros. And so on layer 1 and 2, when you get to the second layer, you're talking about a frame, the unit of measure for that bundle or chunk of ones and zeros that are created with pulses of electrical signal or pulses of light in the case of fiber optics. Those are called, the unit of measure is called a frame. And then when you open that frame up, embedded inside it is a payload, the contents of a package, right? And when you unwrap that frame and open up that frame, inside of it is a packet. The packet is a slightly smaller bundle of ones and zeros. And the packet operates on layer 3, and the packet is what makes IP addresses possible. What am I saying? Layer 3, the network layer or internet layer. So if you're working in industry with Cisco on the internet layer or layer 3, if you're a computer scientist or computer engineer on the network layer, layer 3, same layer, different labels. What you have is the IP number and subnet mask. So all of this, that's the that's what's used to assign a send and receive address on the packet. So a packet is a smaller package or bundle of ones and zeros, and it has a to and from address, just like a package or an envelope in the US mail. So the sender has an identity and address, and the receiver has an identity and address, and it's in the header or on the outside of the envelope or capsule, the digital capsule. Those embedded capsules, when you're traveling up and down the stack, when you're doing this, right now I'm sending images to you in Zoom, and those ones and zeros used to compose the graphics you're seeing right now is on the application layer called Zoom. And those are being sent through TCP because I have a connection to a server somewhere. And when TCP is finished transporting those packets of, well, actually they're called datagrams. So when you get up here, it's called datagrams. When you get to the internet layer, it's called packets. When I get to here, it's taking that packet and it references it basically sticks its own IP address on the header of the packet. And if it's sending it to the server where you can retrieve it, it's going to put the address of the server as the destination address. So IP network addresses are used twice on a packet, the sender and the receiver. That's how we keep track of who's sending and who's receiving. If you've ever wondered, how is it this stuff gets where it's going? That's how it does it. Now, when that's ready for transmission on the wire, it's tucked inside a frame. So we start with a datagram here. The unit of measure for the ones and zeros in the application layer is called a datagram. By the time we get to layers 3 and 4 for TCP/IP, it's called a packet. And it's tucked inside or encapsulated inside a packet, and it's given an IP address, sender and receiver. Then it's stuffed inside another container called a frame, which has to do with the signaling on the wire. Once it gets to the other side, it's unloaded from the frame. The packet reference address is inspected so it can tell, oh, I'm supposed to be at computer 2. So the address for computer 2 is the destination address here. And then that's unloaded so that you can see the digital information that we're sharing right now. So the reverse process happens on the receiving end. Sending end, the chunk of digital information gets bigger and bigger and bigger as it works down the stack of protocols. When it travels across the wire and it gets to the other side, it gets smaller and smaller and smaller until it reaches the application you're using to view it.
A question. I'm sorry. I have a question.
Yes.
I don't know if this is just for emails, but when computer 1 sends information to computer 2, doesn't have to ask permission, like in the sense that it sends the fact that it's going to send to computer 2 information from computer 1. Okay, we get that. And then once the computer 1 gets the confirmation, that's when they send the packets.
So the idea of permission, that's a great question. And to answer your question, no. There is no permission between computers on this scale of network. The only thing that's operating is the addresses. So think of it this way. If there were hundreds of computers and they all said, hey, we hate computer number 2, they could all at once send thousands of packets to the same address, computer 2, and what do you think would happen to the network on computer 2?
It's like a DDoS attack. Yeah.
Yeah, it's called
it's like sending too much traffic.
Denial of service. It's called a denial of service attack. So permissions works differently. when you're working with files and directories inside a disk drive, you have a chance to specify permissions and which account, which user, which computer gets to do what, read, execute, modify, or change. You can control permissions on the file system, but what we have in a network is a transmission system between computers, and the to and from transmission and receiving packets, they all behave according to the protocols. So there are safeties or safeguards in the protocols, um, the the specifications and criteria for the protocols. There are ways to prevent unintended problems and to deal with errors. But that's something that we're actually going to explore more in our next modules. And you're going to build some network applications yourself. So before the course is over, you're going to create a network app from scratch. But then the other thing you're going to do too is you're going to build networks, whole networks from scratch. Okay.
Is this network that we're building from scratch, is it going to be using a specific language? Or are we just going to use like,
We're going to use Packet Tracer, which simulates how a network works. But then in the last module, we're going to use actual computers and actual networks to put stuff out on the internet.
okay,
So we're going to use a simulated environment with Packet Tracer, and then and that network works just like the real thing. And then you're going to see in the last module, holy buckets, I just built like my own domain name and my own web server and my own, wow.
so basically we're using like HTML, right?
Oh yeah. You'll be taking advantage of HTML to demonstrate that you have a functional web server and clients can connect to it, and they can connect to it using a name instead of a number. That gets to be an important topic. We don't use numbers except to set up the network infrastructure so that people can use names. You connect to Buck's Wi-Fi, and then you log into the My Campus portal, right? And you do things by name. That all requires web stuff, email stuff, messaging, social networks. They all need DNS, the domain name system. And we're going to talk about how that works and what it does and how to hack it and how to protect it. So actually, I think your question about permissions was a really well-timed one. Thank you for asking that.
No problem. And when it comes to the DNS, is it like you know how uh colleges they ask you like if you're gonna play a video game, you have to go through the whole talking to people at the front desk of the network association of the building, and they're like, we have to cross it through and add it to the DNS server.
Yes. So
Okay.
what you're talking about is, and it probably involves some network address translation, but what's happening is that your gaming system, if you're doing network games, usually network games have a host system, right? So somebody's gaming platform is designated as a host for a specific game. That's how it works sometimes, depending on the game, right?
And it wouldn't have anything to do like if you were to put a VPN on it or something like that.
Well, we'll talk about
Like,
VPNs, but yeah, VPNs are kind of a workaround that can get a little tricky. The point is that you need a public network address. If you're going to participate in certain kinds of gaming, you need a public address. And so when you're coordinating for your own network address, you that's a required component for the way that game software is rigged. There are
gotcha.
better ways to stage network gaming, and by the time you finish the course, you'll know about best practices versus, okay, what people are commonly doing. And oh my gosh, If you have a gaming platform in a house and it's not set up right, everybody suffers. And one good example of this is you have a gaming platform at your house and you have a game and it says, hey, you got to go on your Wi-Fi router and just turn off the firewall because it's in the way. And some people do that. They turn off the
Yeah.
firewall on their wireless router, and I'm like, really? No, no, you can set up the firewall so that it passes that traffic only to your gaming console. And then that way, what? The rest of your computers aren't sitting ducks on your network. So
If
that's
I
the,
may ask, also, what router do you also have? If I may ask.
well, I have an ASUS router, but
And does it come with like a firewall you have to pay for, or like
no,
part of the? No.
no, yeah, Netgear, D-Link, TP-Link. There's all sorts of decent brands, and we're gonna spend some. We're gonna do a deep dive on that. So I like your questions, and just hang on to them for now because what we
All
want
right,
to
no
do is,
problem.
yeah, we want to do this, and then we want to get to that. We want everybody to get a first crack at the Module 1 assessment. So we have like 3 more pages and 3 more minutes, but we've been talking about some of this stuff already. This is a hand-drawn picture of the encapsulation process. So when you have the signal on the wire at the physical layer, you're down here in the physical and data link level, layer 2. So L2 means layer 2. And the chunk or bundle of ones and zeros is referred to as a frame. And the frame has a header. The header includes the MAC addresses of the system it's on, and it can also have the MAC address of where the frame is going or sending. So it's kind of like that send and receive address on a package or on an envelope with the US Postal Service. The entire chunk of information in a frame is referred to as the protocol data unit. And that on layer 2, the protocol data unit is called a frame. But inside the frame is a payload or the contents. Think of it as okay, we have the box, and on the outside of the box, we have a send and receive address. And on the inside of the box, we also have a packing list. Have you ever received a package from Amazon? You open it up and there's a packing list inside?
Yeah, of course. Yep.
Okay. So how do you know everything came out of the box correctly? You look at the packing list, right? You say, oh, what did I get from Amazon? I have 3 items here, 2 items of this, 1 item of that, 6 items of so-and-so. That's on the packing list. That's what this CRC is on the tail end, on the end of the protocol data unit or frame. We're going to repeat that term over and over again because at each layer, the protocol data unit is called something else. So we're just talking about terminology so you're aware of how the OSI model and 7 layers, the terminology that's associated with this, right? So when you open up the frame, the payload is also called the service data unit. Think of it as the contents of the box. In each case, at each layer, the SDU represents what's inside the box. The PDU represents the box itself. Has anyone ever seen a Russian doll? You know what a Russian
the Russian nesting doll. Russian
Yeah.
nesting doll.
So you have a little doll inside a larger doll, inside a bigger doll, inside a really big doll, right? That kind of thing, right? So the contents, right? On layer 3, the PDU, the protocol data unit on layer 3 is called the packet, right? That's the term for it. And it fits, that whole thing, the packet fits down inside this, right? But when you pull it out, it also has a header to and from with IP addresses, not MAC addresses. MAC addresses are here. IP addresses or network addresses are here. So we have send and receive network addresses. Then we have a payload or a service data unit inside here, the contents of the packet. The contents of the packet, when they're pulled out, are called a datagram. So the PDU on layer 4 and layer 5 and layer 6 and layer 7, from layer 4 through layer 7, the common term is datagram in each case. But the contents inside are always referred to as an SDU. So if I say, what is the SDU of a layer 2 frame? You're going to go, oh, he's talking about the contents inside that frame. Oh, that's called a packet. And when I take the packet out of the frame, I have what's in the packet. There's header information, send and receive network addresses, then the contents of what's inside, the email, the database record, the graphics file, your Netflix video, all of that, right? Your text message. That payload is called the SDU. And how do we know it all gets there? Well, there's a packing list, commonly referred to as a cyclic redundancy check, or commonly called a checksum. It's a digital packing list, basically. So when the payload is unpacked, the box is open and the contents are spilled out, the network protocol says, hey, did we get everything here? And if we didn't, then what happens is that it gets sent all over again. We'll talk about that at another time, but that's what we're talking about. This process of putting a piece of digital information inside a bigger piece of digital information, inside a bigger piece of digital information, inside a bigger piece of digital information, and adding separate details along the way so it knows how to get there. Did you know that when you take your FedEx box or your postal service box to the post office, when they take it to the post office and they ship it to a distribution center, they put it inside another container? Did you know that? Like the containers that go in container ships?
Oh, okay. I guess
Yeah.
that makes sense.
Yeah. And then they take all those containers and they do what? They put it inside an even bigger container called a cargo ship, right? You get what I'm saying, is that when you think about it in the physical world, the same thing happens. You have a box you're sending to your grandmother. It gets put in a postal truck, which ends up in a container, which ends up in a cargo ship. And then on the other side, it all gets unpacked. And how does it get to your grandmother? Well, they have packing lists. They have shipping documents the whole way for each level, and that's what they do. In the digital world, this is called encapsulation. And that's a really important concept. But here's the basic picture of it. And there are slides in the publisher, Comer, has a slide showing encapsulation. Now, when you collapse all of this in here, what you end up with is frame header, and then packet header, and then datagram header. Once they're all inside of each other, you can basically parse out, all that information. The thing to understand is that the term PDU and SDU are used over and over again at each layer. But what they stand for changes at each layer. So the PDU for layer 2 is called a frame. And the header is made out of MAC addresses. The PDU on layer 3 is called a packet. And the header is made out of IP addresses. And the PDU at layer 4 is called a datagram. And in the header, it actually has TCP header information to basically handle the transport, how it's transported, how the data is transported. That's the transport layer, okay? So there's information about how it's transported, whether it's TCP or UDP or ICMP. There are all these related protocols. On the physical layer,
So wait, so Professor,
yes,
quick question. So between layer 3 and layer 4, the TCP IP is split up. So layer 3 deals with the IP while layer 4 deals with the TCP.
yes. In layer
Okay.
in layer 4, the header will say, oh, I have TCP here. Or the header will say, I have UDP here. Or I have ICMP here. There are different kinds of IP packets, and how they're transported works differently depending on the transport layer specifications.
Okay.
And that's important. We're going to get to that later, but you have two types of sessions you can form between servers and clients. And a lot of that depends on which protocol you're using at layer 4 with the datagram. If it's TCP, there's a constant connection that's maintained. If it's UDP, there's no constant connection maintained. The data is just sent. And if it gets there and it's received there, then great. If it doesn't get there, doesn't matter.
But okay, so these protocols, at least the TCP IP, UDP IP, they can still communicate with each other, right?
They can communicate with like types. That's a good question. So TCP packets or IP packets that are rigged for TCP transport can interact with other TCP datagrams that are rigged for the same type of transport. Okay. So
Okay.
the type of datagram that's used on layer 4 will determine how it's transported between systems, either with a connection or without a connection, that kind of thing. Takes a little more time to explain. And trust me, we'll get into it. So did that answer your question?
Oh, yeah, definitely, definitely.
You can't have a network whatsoever if you don't have the data link layer, layer 2, with the MAC identity. It's important to understand this. Networking really begins, your ability to connect and exchange data really happens on the data link layer. And you will find a MAC address in other kinds of network methods like Bluetooth, infrared transmissions, something called Zigbee, a new type of broadband called WiMAX. Oh, hello, 4G cellular. Have you heard of that?
Yeah, 4G. I have it on my phone.
Near field communication, when you hold two phones next to each other and you beam a whole lot of data real quick, you just hold them next to each other. It's called near field communication. These are different kinds of radio transmission, not just Wi-Fi. The important point to remember is none of that works if you don't have a MAC address. And remember, those have to be unique, right? So this last piece, I think what we're going to do on Monday, we're going to spend a little time talking about how the MAC address is used or leveraged to get an IP address. But basically this protocol, let's see if I can do this in like 30 seconds. This protocol assigns the IP address as long as there's a MAC address to start the transmission. The MAC address is the first thing that broadcasts and says, hey, I need an address. So the MAC address allows a device to broadcast, hey, I need an address. The dynamic host control protocol on that network answers that request. So it responds back and something has to run the DHCP so that a device can receive a network address. And that's an important part of.
So this MAC address, is it determined in the beginning, like from when you buy whatever device?
Yes. Each manufacturer
Okay.
and brand, they have their own they have their own MAC address range reserved.
Okay, and then also like what about a Wi-Fi adapter?
The same. If the
The
Wi-Fi,
same, okay.
yeah, if the Wi-Fi adapter has a network capability, then if it's made by a certain company, you can identify the company or manufacturer based on the first characters of the MAC address.
Hmm. So
So,
it's like mostly specified for.
oh yeah, you can look at a MAC address and go, oh, that's a Mac, that's an Apple computer. Oh, that's an Android smartphone. Oh, that's a Dell laptop, because they all have their own starting range of addresses, and then they have the rest of the characters to fill for all the devices they manufacture. So that's a great question. In any case, yeah, all right, so let's go ahead and commit to finishing one more class on Monday before we push the assessment out there. But you have to promise me that you're going to complete your first attempt before Wednesday. So you have your first attempt of the Module 1 assessment completed before the end of the month. And then we'll review the questions on the assessment, and you'll get to reconcile and then log a final attempt, okay?
Yeah, sounds good.
Any questions before we close? I know we ran a little over, and I apologize for the late start of class today. There were some unexpected deflections, but we will do better in the next month to start more on time and end more on time, especially for those of you that need to catch a lunch or catch the next class. So hope everyone
I guess my only question is kind of,
go ahead.
yeah, it's kind of piggybacking off of what Desi asked
Okay.
about, I guess, being about, what do you call it, permission between you and another computer, right? Or another person on the network.
Yes.
Is that the same idea as the allowing your computer to be discoverable on the network? When you like, that prompt shows up when you connect to a new network, and then it says, "Do you want this device to be discoverable?" You either say yes or no. Is that the same? Because like in that case, you are giving permission if you say yes, so that other devices can connect to you, and that
Well,
makes you more vulnerable or open.
so it's a little, all right. The short answer is it's related to how accessible your device is on a network. And it's important for everybody to understand, when you say, yes, I want to be discoverable, you're saying that you want your computer to use a set of protocols so that others can find it. And any system that can be found can be interacted with on a network, whether you like it or not. The question is,
Right, exactly.
the question is, and most people don't get this, firewalls don't protect. See, if I wanted to connect to your computer right now, and I could look up your IP address right now, and I can, but I won't, because it's considered courtesy not to do that kind of stuff. The thing is, if I attempt to connect to your system always has the right to say, no, I don't want that connection. If you're not running a service and the port isn't open and listening, I can't just open a port. I can't force open a port. But if you're running a service that has a port open that's listening for a connection, that means it's available, right? Like, let's say you set up a website on your PC right now, okay? Right now.
Mm.
And you can do that by checking a box, one box, and all of a sudden, bam, you can put a website on your machine, and surprise, you're a web server. One box. That starts a service. It runs the HTTP service on your laptop, and that opens a port 80, And that port is a known port. It's advertised, which means everybody knows port 80 is used to connect to a website. So when somebody has a web browser and they know that your system is on there, they can put the IP address of your system in their web browser. And the web browser will say, oh, let's see if port 80 is open, because that's what web browsers do. They connect to web servers. And the most common port that everybody knows to connect to on a web server is port 80. If your web server is running and the port is open, your machine is going to go, oh, I have a customer. It's going to respond when another device tries to connect to 80. It's going to say open for business. I mean, that's why I'm running the service. That's why I have the port open. Now the two machines are connected. Now all sorts of things that happen after that can get interesting, good or bad. Okay. Does that help explain a few things?
Yeah, it definitely helps clarify the difference.
Yeah. Sure. Now let's say you don't have the web server on there. You don't check the box. On your system right now, the web server service, HTTP, is not running. So it's not opening a port on 80. It's not advertising, hey, I'm open for business for web traffic, right? So even if your machine is discoverable on the network, people come knocking with a web browser, they're not going to connect to your system because there's nothing open on 80. Now, if you turn off your firewall, that's still true. A firewall is good at refusing unsolicited connection requests. So let's say that I want to hack your system and I take some interesting malware and I assign it to port 80. I assign it to use port 80 because I'm thinking, yeah, if you have that thing turned on, I can get to you. Like if you have a web software for your printer, you're running a web server. How many of you knew that? Right? A lot of people don't know. Oh my gosh, if I'm installing this web portal for my printer, yeah, you could be running a web server on your laptop and you don't even know it. Well, let's pretend that you're not, and somebody tries to hack you. You're even without a firewall, your own system will say, nah, that's not, I don't want anything on port 80. I don't want a connection from you, right? So your system can still refuse connections even when a firewall isn't active. But a firewall is an extra layer of protection because when a firewall is in place, it's going to refuse connection requests unless you have certain rules to allow certain types of connections. What most people don't realize is that whenever they install software, the software automatically changes the firewall to open ports for that application. So you can have so many holes on your firewall, it's like a screen door in a submarine. This happens a lot for gamers or for people that enjoy bootleg content and they like downloading from Tor, from BitTorrent. I mean, let's just keep it real, right? There's a lot of stuff on the internet that people access, and once you load it all on your system, some of those things open holes on your firewall. So the holes remove the protection the firewall would otherwise provide. Having a machine that's non-discoverable on the network means it's harder to get to, it's harder to interact with, and it's harder for hackers to lay hold of. So it's not about permissions, it's more about hiding in the network environment or exposure in the network environment, if that makes sense.
No, I think that does.
So, I mean, are you removing permission to interact with your machine? In a manner of speaking, you are, because if you're saying, no, I don't want to be discoverable, in a sense, you're saying, yeah, I don't want to put my stuff out there for everybody to see it, because that's just an attractive nuisance.